Thank you, Selwyn. Thanks. Thanks to the organizers, well, Selwyn, WUH. It's a great pleasure to be back in Singapore. I feel like I'm among friends here with Selwyn and WUH Wu and CT. And it's a special pleasure to be part of the celebration of Rod Downey. Rod and I think, started working together probably 30 years ago at the Special Year in Logic, MSRI. We worked on Pi 01 classes. We also had a project we were working on with complexity and model theory. It took many years before this actually came out, but there is a paper, and it turns out this is related to abelian groups. So I will say something today about abelian groups and the connection with homogeneous structures. So let's see. What I like about this topic, it connects up a purely model theoretic or mathematical notion that connects up with computability. So I'm using the term ultra-homogeneous. So, Dennis just talked about homogeneous. It's the same concept. It's the word homogeneous is used for so many different things. So ultra-homogeneous is kind of emphasizing that we're talking about this concept. So we generalize a bit from ultra-homogeneous to a weakly ultra-homogeneous. You'll see it's a natural idea. When we've been working on the computable and other categoricity of structures, we always have some finite set of parameters that are allowed to help us with our definitions, with our constructions. And the weakly ultra-homogeneous simply adds in a finite set of parameters, as you'll see. So we can apply this to some well-known structures such as linear orderings, equivalence structures, trees, injection structures, and make a comparison with our notions of effective categoricity. So this was joint work with Francis Adams, a recent graduate from Florida, and last year Selwyn also joined the project. So let's get it. So there's some connection with this idea of the Froussé structures, where you have a family of finite substructures, and you take the limit, the Froussé limit, to get a homogeneous structure. So I'm not really going to say much about this notion of the age. For example, if you look at the standard ordering on the rationals, then the age of this would be the set of finite linear orderings, and then Q can be viewed as the Froussé limit. If you look at the Boolean algebras, you could look at the subsets of the natural numbers, and then the finite structures are just the finite Boolean algebras. Okay, so that's kind of certain properties of ages. So put this in the context, but so I won't be really talking about these, but some background. If you're familiar with these Froussé structures, this won't really come up in the talk, I think. Okay, so the Froussé limits. So Froussé said that a structure should be ultra-homogeneous. As we saw, if any isomorphism between finitely generated substructures extends to an automorphism of the whole structure. So in case you have a structure has functions, then you're not just looking at the points themselves, but also the closure under the functions. And Froussé showed that you always have a countable ultra-homogeneous structure if you have such an age. And you say the examples. The countable dense linear ordering is the Froussé structure for linear orders, and the countable atomaless Boolean algebra is the Froussé structure, the limit of the finite Boolean algebras. So the dense for those examples. Okay. And the key, I think, Dennis had a slide where he talked about that too. It's enough to say that you could extend from a finite isomorphism to an automorphism of the structure. It's enough to say that you can extend it one step at a time, essentially. Okay. So that's well known. Okay. Yeah, so we already saw that. So some other examples. We have the random graph is the limit of the family of finite graphs. For equivalent structures, you would want a structure that had orbits of every, to be homogeneous, you want orbits that have everything having the same size. So we'll see that. And we're talking about injection structures. To be homogeneous, you have to not have orbits of type omega. Okay. Right. Okay, so we'll see. So if you have a type omega orbit, the problem is if you're looking if you have something like this, and then if you take, so if you start here, you're only mapping forward. If you start at the beginning, you map forward. Well, then these two things are isomorphic when you close up under the function. These are isomorphic, but this is the whole set. So it's not possible to extend that isomorphism. Okay, so the natural numbers with the successor function is not homogeneous. And that if you have z under successor, and then this is homogeneous because every pair of points is automorphic. So that's just to get an example. Okay, so we define the notion of weakly homogeneous to say that you have a finite exceptional set of these parameters such that when you fix those parameters along with some pairs, some elements x and y, then this finite isomorphism can always be extended to an automorphism of the structure. And equivalently, you could just think of adding names for those elements to the language, and then this becomes ultra homogeneous. Okay, so we want to make a connection with categoricity. I think we've seen this in other talks. A structure is computably categorical or delta 2 categorical, provided that every computable structure which is isomorphic to A is computably isomorphic or delta 2 isomorphic, and so on, to the structure. Okay. And we also have the notion of relatively categorical. If for any two structures which are isomorphic, there's an isomorphism which will be delta 2 or computable relative to the diagrams of those structures, which is a bit stronger. Okay. So the main result that we could show, the main computability result, every computable weakly ultrahomogeneous structure must be delta 2 categorical. So I have a sketch. Basically, you can see you can start with going with a back and forth argument. When you have a finite automorphism that you're building, then you extend on one side, and then you have to look for, okay, you have to look for the element on the other side, and then testing whether these are isomorphic. These are now infinite structures, so it's potentially a pi01 check to see that these finally generated structures are isomorphic. And then you can build back and forth to get those. If the this should be a finite language. I mean, one could generalize, but we're thinking of yeah. I guess if the language is computable, it should still be okay, right? Because you're just going to do finitely much at a time. You would be generating a finite piece at a time, but I'm not, okay, that's, yeah. We only looked at finite languages, okay. Only at finite languages. Finite first order. Okay. In most cases, so when we started looking at it, it seemed like it was, in a lot of cases, it was just the same as computably categorical. So let's look at, in particular, if you have a relational structure, or more generally a locally finite structure, where every finite set would generate a finite substructure. So for example, if you have a torsion group, then a finite number of elements, because everything has a finite order, that you'll get it will generate a finite subgroup. So a structure like that, then the argument shows that these would actually be computably categorical. Because you close up, you get a finite structure, and you can test whether those are isomorphic. Okay. All right, okay. But I guess I'm thinking this example of, yeah, certainly when you look at, I can't think of a zero, but I guess, yeah. You can have something which is computably categorical, but not necessarily homogeneous. Okay, I'm not sure which example I'm thinking of here. Yeah, so the z, the omega, once you give a name for the initial point, let's see, that's going to become, okay, that's not the example. Okay, I'm sorry. Okay, let me just see. Okay, that is not. Okay, so, all right, so we want to look at a number of examples and see what the connection is between the being homogeneous or weakly homogeneous versus being categorical at various levels. So for computable linear orderings, it's well known that the computably categorical structures are those which have only finitely many successivities. So you can picture this shape of having a finite number of copies of the rationals and then finitely many points put in between or on the end. And then we show that this is equivalent to being weakly ultrahomogeneous. If you simply give names to all these finitely many points, these special points, exceptional points, then any finite isomorphism can be extended to an automorphism. So then here we see that each one of these structures, of course, has a computable model, right? Since you have finite sets and then you have copies of the rationals. So every weakly homogeneous linear order is essentially computable or has a computable copy. So that's an example of just a model theoretic notion, then it leads over into computability. Okay, and yeah, so this turns out to correspond exactly with being computably categorical. So for linear orders, weakly ultrahomogeneous is exactly the same as computably categorical. So now we started thinking, well, so is that going to be true in every case? So we'll look at some other examples where it can fall in between computably categorical and delta 2 categorical. Okay, so this is the classic case. Naturally, we couldn't resist thinking about index sets. What is the complexity of this notion? So it's not too hard to show that the ultrahomogeneous linear orderings would be a pi 0,2 property, being ultrahomogeneous. Being weakly ultrahomogeneous then would be a sigma 3 property because you're asking for the existence of these parameters. And you can demonstrate the completeness. We did that. Of course, the underlying family of structures being a linear ordering is going to be pi 0,2 of itself. Any type of structures, you're going to have pi 0,2 property because you need to say that you have a total function, a total computable function. Okay, so we have results of this sort of index set results for most of the families. I'm not sure I'll list all of them, but okay. So then injection structures, as the picture for omega, we have a set, say omega basically, and some type of one-to-one function. Then such a structure can be partitioned up into orbits. You can have finite orbits, and you can have these omega chains, finite, and you can have Z chains. So there's 3 types of orbits you can have with an injection structure. Here we can focus on the character as describing how many orbits you have of various finite types. The 2 types of infinite orbits you have, there's some certain number that you have, but that's just a single numbers. That doesn't involve the complexity. And the character in this case will be a CE set, and you can get any CE degree basically here. So let's see. Okay, so in this case again, the ultrahomogeneous structures cannot have these omega orbits for the reason that I kind of expressed earlier. If you have no omega orbits, then you will be ultrahomogeneous. Then weakly ultrahomogeneous naturally just said that you were allowed to have finitely many of these omega orbits. So the key here is the finite types. The finite orbits, you can recognize them, right? If you're given some finite orbits, well, you just keep applying the function until you come back where you started, and then you can recognize those. Those will be preserved under the isomorphism. So it's only the infinite orbits that could possibly cause a problem, and in fact, it's only the omega orbits. So how does this compare then with the categoricity? So some earlier work, we showed that an injection structure will be computably categorical if it has only finitely many infinite orbits. That's of either kind. It's delta 0,2 categorical if it has either finitely many omega orbits or finitely many z orbits, but can have infinitely many of one, but not infinitely many of the other. So in this case, computable categoricity implies weak ultrahomogeneity, which implies delta 2 categoricity, but none of those can be reversed. Okay, so this is properly in between. So this is a nice example that shows that the notion of the weak ultrahomogeneous can be properly in between the computably categorical and the delta 2 categorical. Okay, so that was that's how that came out. Let's see. And in this case, one can certainly have, so in the case of the linear order, everything was computable. In the case of these injection structures, because the finite orbits don't matter, you could have an arbitrary collection of finite orbits of various sizes that doesn't have to be computable. Okay, these would still be ultra-homogeneous. So that means that we certainly have plenty of non-computable examples. Okay, I think I'm spelling out. Okay. Yeah, all right. So essentially, this is just saying the character, the number of finite orbits of various sizes is kind of irrelevant to this question of whether you are categorical. So you can actually say that these structures, the non-computable structures, can still be viewed as relatively categorical. In the sense, any two copies of them would have an isomorphism computable from the structures in a delta 2 fashion. Okay, whether they're computable or not. Okay. And then, yeah, the index set results come out to be essentially the same as for the linear order. So being homogeneous is still pi 2 because you're essentially saying, given these finite many parameters, can you always get an isomorphism? Can you always extend one step at a time? So does there exist one more level of the isomorphism? And being weakly becomes sigma 3 complete. Okay. So injection structures. Then going back to a kind of a simpler case, the case of equivalent structures, then being weakly ultrahomogeneous is quite naturally that it's all but finitely many equivalence classes have the same size. And in this case, we go back to being weakly ultrahomogeneous if and only if you are computably categorical. Okay. So that is, that's a very natural. And again, the index sets, they still come out at the same level of the pi 2 and sigma 3. It's not entirely trivial to get the completeness, but anyone can do it, basically, I would say. Okay. All right, so more recent work, we worked on trees. Of course, trees have many different ways of being interpreted, right? We're thinking of a tree with a root, trees that are essentially could be viewed as a subset of omega less than omega. So you could have countable branching or finite branching. And one way to look at it is simply a tree as a partial order of extension. Another interesting way turns out to be looking at the tree with the predecessor function. Okay, so in either case, because the predecessor function is going downward in the tree, you'll have locally finite structures. And then we're interested in looking at the tree above a given node. Okay, and also the tree below a given node. Okay, so that's sort of two important concepts to think about. So this becomes it's kind of trivial in the case of the partial ordering, but when you have the predecessor, it turns out to be quite interesting. Okay, so I think we all know about trees. You can think of these two notions that the height of a node kind of starting from the bottom up, how far up do you have to go? And then the rank is kind of going down from the leaf. You have a leaf node of a tree with no extension that has a rank 0, and then as you go back down, you're taking the supremum, so that when you have an infinite number of branches, potentially you can start having a transfinite rank. Okay, so the rank of the tree could be any countable ordinal, and for a recursive tree, of course, it would have to be a computable ordinal. Okay, so standard notions. So then Russell-Miller showed that under the partial ordering, if the tree is computably categorical, it can only have finite height. And Miller, Reed, and Charlie McCoy characterized the computably categorical tree as a finite height. A fairly complicated notion, which we also have some complicated notion that I may not want to really talk about, but they did that characterization. So what about the weakly ultrahomogeneous version? So this becomes really too simple. To be ultrahomogeneous, you have to have rank less or equal to 1. Okay, so essentially you have the root, and you can have some points above there. You can't have any more because, you know, under the partial ordering, if you just had one of these and then you had one like this, then somehow, you know, these two, if you look at these two nodes, they look just one is above the other, and you look at just these two, just leaving that out. So this one and the one that's above there, they look the same, just 2 points, one is above the other, 2 points, one is above the other. But if this guy has a node in between, and this pair doesn't have a node in between, then of course it's impossible to extend that to an automorphism. So in the partial order, doesn't give you enough information about the finite structures to be doing anything. Then weakly ultrahomogeneous, then we first showed that you have to have finite height, and then in fact the characterization, you can only have finitely many elements of rank larger than 1. So you can have arbitrary height as long as only finitely many get above rank 1. So again, we have this, in this case, we have the situation that every one of these has a computable copy. And certainly every weakly ultrahomogeneous tree has to be computably categorical because they're locally finite. So these are not so interesting. Then under predecessor, I think with the predecessor you can determine the partial ordering, okay, because you just take each node and go down to the root, and then along the way you're going to see that if one is above the other. So yeah. This is a more general notion. What am I thinking? Yeah, so if you right. If you have a tree with a single infinite path, then under the predecessor, this should be ultrahomogeneous. Okay? Because given two points you generate down, and you just count. If you have the same number of points on your path, then you're the same point. It's really basically rigid. Okay. So now we have. So under the predecessor, being ultrahomogeneous has this simple characterization that any two nodes of the same height must have an equal number of successors. So that means at the bottom level, maybe you have omega branches. At the next level, every one of these branches must have, say, the same number of extensions. Let's say they all have exactly 3 extensions. You have 3, 3, 3, 3, 3 all the way across. And then from those 3, now you're limited. You could only split those up into, let's say, all into 3 of size. Let's see. Each of those could have 2 branches, let's say. And then above that, every pair of those branches could have omega branches again. So you can take essentially any infinite sequence of finite numbers and omega and create an ultrahomogeneous tree. So there's going to be continuum many of these already. And then to be weakly ultrahomogeneous, okay, there's this a bit complicated notion a la the Lemp et al. Paper. So maybe I don't have time to give the details or some more interesting things, but so we can characterize the weakly ultrahomogeneous trees looking at this notion of the tree, which essentially you're looking at the guys that are below a point and together with the ones that are off to the side somehow. Okay. So there's a notion under which it's weakly ultrahomogeneous, provided that when you restrict from every node, you can come up with an ultrahomogeneous tree. Okay. So in particular, it would work if you had a sort of a finite tree, and then below every one of those or above every one of those nodes, you had an ultrahomogeneous tree. That would be an example of being weakly ultrahomogeneous. But it's a bit more general than that. So, okay, don't say too much. So in particular, you can look at the trees of low height. So for height less or equal to 2, being weakly ultrahomogeneous is saying that all but finitely many of the nodes of height 1. So at height 1, you have some number of branches, finitely many or infinitely many. And then almost all of those have the same number of extensions. So that's fairly straightforward. So the exceptional set could be those that are different, right? You could have the different ones. So you might have, and then there's a, let's say mostly they have 2 extensions, but then you have a few that are different. This might have, omega, but mostly they should all have 2. So if they almost all have 2 extensions, just a few exceptional ones that have a different number, then that's going to be weakly ultrahomogeneous. I think, okay. Yeah, so this actually becomes different than it's different than computably categorical. Of course, if it's weakly ultrahomogeneous, it has to be computably categorical, but there are other ways in which a structure could be categorical without being weakly ultrahomogeneous. So let's see, maybe a picture would be of this story. What am I thinking here? You have, yeah, so you're kind of splitting up into 2 flavors. Yeah, so you have the guys that, I think some have 2, and some have 3. Okay, yeah. So some have 2 extensions, and then some have 3. Some have 2, some have 3. Okay, so some have more, but when you turn it around, then the one where you had fewer, then they have more. So the guys with 2, let's say they each had 4. And the ones with 3, they had only 1, maybe somehow. Okay, so this fails to be weakly ultrahomogeneous because there's sort of infinitely many of 2 different flavors. But it's computably categorical because you can recognize, you're able to recognize where you are. Okay, so you know that you're a 3 node when you see three paths branching out. So you know you're there. The danger when you see 2 is that, well, maybe there's going to be a 3rd one later. So how do you know that doesn't happen? Well, if you're on a 2 node, you look above, and as soon as you see 2 paths above there, 2 branches there, you can't be a 3 node because those only have 1 extension. So then you know that you're a branch, you're one of the guys that you're not going to have a 3rd one. That allows you to build a computable isomorphism. So these things can be not homogeneous, not even weakly homogeneous, but they're still computably categorical, so kind of playing on the structure. Okay. The idea there is just that when you have the maximum number of branches, the bigger number, you know it when it happens. You wait for that to happen. If you have the smaller number, well, you can just look one more level, and then you're going to have the larger number there. So this becomes still computably categorical. Okay, so this is a difference. Okay, so we want to we'll come back to trees. I want to look at extending the notion of equivalent structures to nested equivalent structures. So nested structures is where you have several equivalence relations, and then each additional one is an extension of the previous one. It's larger. So you can think of starting at the beginning. You have all the numbers are equivalent to each other. You do your first equivalence relation. It partitions into various classes, and then the second equivalence relation takes each one of those classes and partitions it further. Okay, and you can see here that there's some connection if you have an n-equivalent structure. If it's ultra-homogeneous, then each of the individual ones have to be ultra-homogeneous. Okay, let's see. So you have a similar story here about things in the nested structure which can be computably categorical but not weakly ultra-homogeneous. It's kind of similar to this picture. I have the different story there, but it's essentially the idea that when you're splitting, when you're dividing the classes, you can, yeah, okay. I guess this sort of speaks for itself. Huh? Okay. So you have different sizes, I guess. Yeah, this is I think this is an example, right? So these are not nested, I guess. So maybe that's not so interesting. These are not nested, but okay. So if you take these two single points by themselves, they have to be isomorphic. They're just only related to each other. But then in the single point one ends up with together with two. Yeah, I guess that's right. Okay. Yeah. So when you look at these three. Okay, yeah. They have different sizes. Okay, so this is a simple example. So we found a nice connection between trees and equivalent structures, and I'm just going to make another picture. Well, we didn't find this. This was discovered, I think, by Valentina's student, Leah Marshall. Okay, so let's see if I can draw this picture that I had in mind here. We're thinking of, okay. So say I have these, thinking of equivalence relations, so we start with omega. Let's say we divide up into classes of size 6 here, 7, 8, 9, 11, 12, Okay, so if we just partition up modulo 6 there, and then from here maybe we split like this. We subdivide each one of these into 3 pieces. Et cetera, et cetera. Okay. And then potentially you can, at the end, you could at most divide everything. So we're really thinking of two equivalence relations. Okay. So under E1, we have these finite classes, and E2 then splits each of these. And then we just kind of have the trivial equivalence relations that we attach onto each end, okay, where everything is equivalent to everything else, and at the end, then each point is equivalent only to each other. So we sort of add an E0, and then at the end, we add this E3, say, where everything is equivalent. So it's only these two. These two are really the two nested equivalent structures. And as I've drawn this, you see that here we have a tree. Okay, so given any nested equivalent structure, finitely nested, you can extend to a root at the beginning. Just look at the order. The partial ordering is inclusion, and at the end, each finite set could be divided up into its individual elements, and this then produces the tree corresponding to the structure. And this can be done effectively. Okay, so again, this is due to Leah Marshall. So what's the connection to the category? So she was looking at the trees under partial orderings. So you have a very nice result that the nested structure will be computably categorical if it's relatively computably categorical, if the corresponding tree under the partial order is computably categorical or relatively. So this was established, and you can see how this will work. So what we did was look at the, extend this notion to the trees with the partial orderings. Okay, so let's see. I guess this is still, yeah, okay, this is sort of explaining the picture there, yeah. Explaining the picture. So what can we do, yeah. So the ultra-homogeneous, let me see. Yeah, so okay, so that's computably categorical, but what about being ultra-homogeneous or weakly ultra-homogeneous? So I think in this setting then, this corresponds to what the trees are doing, right? So this is, but with the predecessor is where something happens, okay? So the equivalent structure will be ultra-homogeneous if and only if the corresponding tree is ultra-homogeneous in the predecessor representation. And of course, we know this corresponded to partitioning that for the tree, you had to have an equal number of branches at every level. Okay. So that is the picture preserves the notion of being ultra-homogeneous. Okay, so now the weakly ultra-homogeneous becomes a bit more complicated, but it's still true that the nested structure will be weakly ultra-homogeneous if and only if the tree is weakly ultra-homogeneous in the predecessor representation. Okay, and then we can use so the examples that we constructed for trees then can correspond here with the example for nested structures. So I think yeah, okay. I have an example, but the example that I erased, okay, the one where you were doing branches of so pairs and triples, and then above the triples you had singles, and above the pairs you had four. The same example. That example could also work here. We don't need another example. That example will carry over from the trees to the nested structures. Okay. All right. So yeah. So that's so this material was in this paper that's going to be coming out in the journal Computability. It's in press, I guess, or it's appeared online. Okay. So then. Last year when Sullivan was visiting, we tried to extend, well, we made some progress in looking at abelian P groups. This is another area where we have a pretty good idea about a class of structures and their categoricity. Okay, so here you have, it's been, I guess I'm just wanting to say somewhere here, the results of Rick Smith and also Goncharov, I'm thinking. Yeah, okay. Goncharov and the group characterize the computably categorical abelian P groups as consisting of copies, arbitrary copies of the divisible group together with a finite group, or particular or finitely many copies of the divisible group together with infinitely many of a particular cyclic group, and then some other finite group. Okay. So since P groups are locally finite, these are the only structures that could possibly be homogeneous or weakly homogeneous. So we just have to determine which ones they are. Okay. And this turned out to be interesting. Okay. So let's see. Was there something? Okay. So this has. You can talk about a character for a group, just like we talked about the character for injection structures. If you have a certain number of cyclic groups of various sizes, that sort of measures the complexity there. Okay, so now let's see. So to be ultra-homogeneous, you have to be either divisible, so you could have the divisible group or some number of copies of the divisible group. Okay. Because there, everything, it's kind of rigid, okay? You know, where given any element, it has a finite order. You simply compute back until you see where it lies in the ordering. And if you have two of these guys at the same level, like 1/8 and 3/8, they each have order 8. They're going to be automorphic to each other. Okay. But the other possibility, this is there's a nice article by Cherlin and Felgner that characterizes the ultrahomogeneous abelian groups. So the other possibility is that it's homocyclic. That is, you can have infinitely many copies of only one particular cyclic group. Okay, you can't have different ones. And that, so again, these all have computable copies. But it's interesting here is something, you can have the failure even for a finite group. So if we have, say, the cyclic of order 2, cyclic of order 4, put those together, this is not ultrahomogeneous because the Z4 contains an element of order 2. Also, Z2 has an element of order 2. Those cannot be automorphic, right? They're not automorphic with each other. So if you have the kind of have a Z2 with 0 and 1, and you have a Z4 and 3, well then, looking at this 1, 0, 0, 2, these both have order 2, so locally they look isomorphic, but this guy is divisible, right? This is divisible, and this 1, 0 over here, this is not divisible. So those cannot be extended to an automorphism. So you have just this simple, very simple finite structures already, not ultrahomogeneous. But it turns out to be quite interesting the way it what happens when you look at infinitely many copies. Okay. So we know the classic example of something not categorical would be having, say, infinitely many of, okay, so in particular, if you have infinitely many copies of Z2 and then infinitely many copies, plus, right, of Z4, this is not, okay, this fails to be computably categorical. So, of course, it fails to be ultrahomogeneous, but if you have infinitely many of one and finitely many of the other, that's going to be computably categorical, whichever way it goes. But the surprising result here is that if you have infinitely many of the larger size and even one of the smaller size, that this fails to be weakly ultrahomogeneous. Okay? So you're just taking this, it's kind of the same example. Now you have lots, I think now you're having lots of these, lots of these, et cetera. Okay, so you can have lots of these. So, sorry, but only one of these. So if this were weakly homogeneous, then there would be some finite number of these, a finite number of elements from this whole part could be given in the exceptional set. So you would have at least one copy where this was not part of the exceptional set, okay, or was not part of that. And then the same argument. So you can just extend this argument a little bit, basically by taking. Okay, so in this case, you're actually looking at the order 2. Let's see, what if I look at A plus B? So I think it's the 0, 1. Right. So you're looking at the element of order 2 then. Right. So now basically I think it's the 0, okay, 0, 2. Okay. So you can look at the elements 0, 2, and 1, 2. Okay, 0, 2, and 1, 2 both have order 2. The 0, 2 is divisible, and the other one is not divisible. So you can just in this piece, you can just map these, leave the 1, 0 alone, and this will be, and then have the identity everywhere else, essentially. Okay? Just do this little trick here. Okay. So you just look at these pairs, the one which is divisible, the one which is not divisible. You interchange those, that's a local isomorphism, and it cannot be extended. So just having even one smaller cycle and then infinitely many larger ones fails to be weakly ultrahomogeneous. But of course, it is completely categorical. Okay, so this was the interesting, surprising, I think, result. The other way it would be homogeneous. Okay. If you have one larger one and infinitely many smaller ones, that's going to be ultra-homogeneous. You just give names to the larger ones and you're all set. Okay, so that is... and a similar argument shows that if you take even the divisible, you take the divisible group and then even a single cyclic group, this will fail to be weakly ultra-homogeneous. You can sort of mimic this in a sense. Because the divisible part has elements of arbitrarily large order, and you can pull this same trick. Okay, so yeah, okay, so it's the same. It's the same idea basically. Basically the same idea. Okay. Yeah. So there's a little, I mean, there's some little technical calculations there to see how high up you have to go in the divisible group to find the element that you can match up with the cyclic part to get something that cannot be extended. Okay, so those were really not expected. We didn't expect this to be true, but that's how it turned out. So you can characterize being weakly ultra-homogeneous. Either you're just divisible, or you can have infinitely many copies of sort of homocyclic part, infinitely many of the same size, and then some finite group, but the finite group must have all of the cyclic groups have larger order than n, okay, of larger order. And then you can see the again, the exceptional set will just take the whole finite part, essentially, the whole finite part. Okay. So in the paper, you know, we looked more closely at characterizing what the exceptional sets could look like, and even the notion of a minimal exceptional set, or what would be generated by the exceptional set. So I've omitted that from the discussion today. Okay. So this was recent work, again, with Selwyn. We also are looking at Boolean algebras. Now this Boolean algebras also have different ways of presenting. So you can look at the language as just being the order on the Boolean algebra, in which case it's just trivial. So being ultra-homogeneous, you could only have 4 elements at most, okay? And then being weakly ultra-homogeneous corresponds to being finite. So the 4-element thing is just so that you have enough structure. It's similar to the trees where you had, you know, if you had height 2, you could have an element and then a gap in between. So that's a similar thing. If you have 8 elements, then you have things. You have sort of 2 levels in between, the 0 and the 1, and you can play those off. You can have the one at the lower level can look the same as one at the next level, but that can't be extended. So, but that's really that's simple. If you have the language that includes the meet and the join, then this is well known, of course, that ultra-homogeneous corresponds to being a dense Boolean algebra. And then weakly ultra-homogeneous quite naturally corresponds to having finitely many atoms. So in this case, being weakly ultra-homogeneous will be identical with being computably categorical, which is nice. So we actually were plunging in and working, getting our hands dirty, improving these things. And I think I realized recently Boolean algebras can correspond exactly to interval algebras of linear orders. And if you look at that carefully, that correspondence is effective. And then the successivities in the linear order will exactly produce atoms in the Boolean algebra. And so I think just playing that back and forth, this becomes a kind of a corollary to the results for linear orders. I believe that we can do that and not have to actually reprove it from scratch. Okay, so that's the recent accomplishments. So obviously there's many other interesting structures, in particular the torsion-free groups. So I have been recently enjoying these Downey-Melnikoff papers that explain a very beautiful theory of the categoricity, computable categoricity, and also the isomorphism problem for torsion-free groups. So we want to pursue that, look at the ultra-homogeneous structures there. And in talking with my student, we want to possibly extend the notion of these trees to trees of transfinite height, which are, since he also is interested in set theory, it's sort of a set theoretic construct that you can imagine trees of transfinite height, and that's so we are interested in doing that. So that's where we're at, and other structures as they appear. So, thank you, and happy birthday, Rod. Okay, sorry.